All right. Hello, everyone. Please confirm if you can still hear me. All right. So I'll start sharing the screen. Okay. All right, everyone. Welcome to the fifth session. Here today we'll be discussing week 6, where we've been taught nonlinear regression, clustering, and classification. Right. So just a quick revision about what is linear regression and what we've learned in week 5. So we have been taught about simple linear regression and multiple linear regression, right? And yeah, and they follow this general equation: y is equal to mx plus c. So a linear relation between this x, which is called the independent variable or the predictor, and y, which is called the outcome or the dependent variable. And in case of multiple linear regression, you can have multiple predictors. So here x1, x2 until xk, and y is going to be the outcome. One important aspect about multiple linear regression is that each of these predictors, each x1, x2, until xk, should be linearly independent of each other and also of the combination of others, right? So x1 should not be 2 times x2 plus x3. This thing should not be there. So this leads to multicollinearity. All right. So additionally, we also discussed about certain diagnostic checks that should be done once you have an equation at hand. You should check if the coefficient of determination is high, if each of the coefficients that you have here, m and c and b1 until bk and a, each of these are significant. The model itself is significant. So all these coefficients of the independent variables, b1, b2 until bk. So we know that for some of these we need to perform t-test, and for the others it has to be an f-test. And additionally, we can also find the confidence interval for the 95% or whatever percentage confidence interval for each of these coefficients. So this was just a revision. Now, in this week, we start off with discussing nonlinear regression. And these are some of the examples of graphs that wherein here on the x-axis, you have the independent variable or the predictor, and the y-axis is the outcome. And you can see that this is not a linear trend. So the way we find out what is the exact equation to fit each of these models is through one of these three methods. In some of these cases, we already know what kind of an equation it would be, whether it's exponential or logarithmic or a simple polynomial equation. This information is required through some prior information, because once you deal with these equations in the field, you would get used to looking at these equations and getting an idea of what could the possible equation type be. And then once we know that, then we find out the exact values of the coefficients. Right. So this was one of the questions asked in the discussion forum, that if we already know what kind of equation it is, how is this method helping? So mainly we want to find the values of that coefficients, right? So we'll see how that's done. So in general, so the first type that we do is where it's a polynomial form, where it is just powers of that independent variable increasing one by one. So this is the form in which you can see this. And if you think about it, each of these subsequent powers can be thought of as a different variable itself. So like in case of multiple linear regression, we had this form. So if you compare the polynomial form and the simple multiple linear regression form, you can just see that each of the powers are replaced by a different variable. Now, one aspect of multiple linear regression that must be taken care of is that each of these should be independent of each other or of a combination of others. But it's not just independence, it is linear independence. So we know that x and x square, they're dependent in a way that one is squared of the other, but they are linear still. They're still linearly independent, right? If you plot x and x square, it's not going to be a straight line, right? So here, that problem is elevated. So we can consider this now as a multiple linear regression problem. And like in that case, we can make matrices out of it. So this becomes the outcome matrix. This becomes our the input values or the predictor, the predictors. And this becomes the values of the coefficients that we want to determine. And then it can be solved by simple matrix calculations, right? Any question until now? So when we have performed polynomial regression and we have found out values of these coefficients, just as was the case with multiple linear regression, each of these can be determined. So particularly the statistical test of significance was discussed in these lectures, wherein the t-test for each of the coefficients can be calculated. And we know that specifically when we talk about how it's done in R, we know that the LM function returns, it performs t-test on each of these coefficients and it returns the p-value, so we can check if it is significant, which means it's lower than a threshold or not. Likewise, the f-test, which was done for all the coefficients of these independent variables, b1, b2, b3, until bn or until bk, that was also done. But another f-test can be done wherein our model, wherein we want to actually restrict the power. We want to see if a quadratic model is sufficient, or should we go on for a cubic model or for a model which has the highest power 4, and so on, right? So this were just a little difference in the diagnostic check. In addition to the polynomial type of nonlinear functions, we can also convert a nonlinear function into a linear form by just simple algebra. So this equation, which you may encounter in case of Michaelis-Menten enzymatic kinetics reactions. So the equation is of this form. If you find out the inverse of both the sides, this becomes 1 by y. This becomes x plus q upon p by x. Let me just write it down. Right? So here you would have 1 by y, and that would be equal to x divided by px plus q divided by px. And if you solve this, this becomes 1 by p and plus q by p upon 1 by x, right? So the new equation can be of this form, that where you consider y is equal to 1 by y, and like a capital X can be considered as 1 by x. And then this 1 by p becomes the constant, and q by p becomes your slope, or m in that case, right? So it's again of the form y is equal to mx plus c, simple linear regression, and then this can be solved. Another way, which is specifically used for equations which would not fit either of these two types, is when you already know the equation, or you know a certain form of the equation with a lot of unknowns. So then, as we had discussed previously, there is something known as residual sum of squares, right? So this is a residual wherein, so you have where you have a lot of data points, x1, y1, x2, y2, and if you have this equation and you obtain, corresponding to x1, you obtain a y1 hat. So this is, if the equation were absolutely correct, you obtain y1 hat, but actually you had y1. So the difference between these two becomes the error term. You square it up so that the negative and the plus signs don't matter. So, and then you sum it up. So sum of the squares of residuals, RSS or SSR. And so this can be calculated for your equation of choice. And then there are algorithms which can find out what value of your coefficients, in this case A, B, and C, will minimize this error. All right. So this brings us to the end of the first part of it, which was nonlinear regression. So I have a few, so let's just go into R now, and we can quickly discuss some of the aspects. This is a quick revision of what was discussed in the lectures with a few changes. All right. So this was so I hope now all of you should be more familiar with R. And I hope you've started writing a few scripts. So even though in the final exam, you will not have questions that require you to use R and R Studio, but if you have if you are in practice and you have been using R regularly, you'll be able to solve them, right? Because some of the questions could be very basic, which are just syntax based. So keep practicing and let me know if there are any questions. Okay, so we'll take a look at this first file, which is a yield from some plant. So we have different temperatures at which yields were measured, and of course there were some replicates for each of these. So this was the so let's just see what is the trend, because if we want to uh, fit any equation which is comparing temperature and the yield of the plant, we would like to see if it's linear, if it's non-linear. So simple, the plot function, first argument is going to be the x-axis and the second argument is y-axis. I've not added the other arguments, which can be legend and which is like the main or the x-axis label or the other things. So if we plot this is what comes up here. So you can see that this is a non-linear trend, of course, and it's something like this curve. So let's say we don't know if it's going to be what power it's going to be. So let's try everything. Let's try fitting a linear model. Let's try fitting a quadratic one, and let's try fitting a cubic one, right? So I hope you can still see the screen fine, right? Yeah, just give me a thumbs up if that's okay. I'm assuming you can see the screen, right? Yeah, all right. Okay, so we try fitting a linear model. So the LM, here the syntax is whatever is your outcome, and tilde the input, and this is the name of the data. So by the way, yield and temperature, they are the columns in this data frame. So we try fitting the model and we save it to M1, and we use the summary function to find what it has returned. So here we see, okay, we have these. So it's going to be of the type mx plus c, where the intercept or c here that says it's significant, and temperature, it says it has this coefficient, but it says it's probably not significant, right? So if at all we have to fit a linear model, then it's just the intercept, right? So now we know that this cannot be correct, because then it becomes a straight line parallel to the x-axis. So we know this model is incorrect. So let's move on to the quadratic model. Now, to write subsequent powers of any of the input variable, there are two ways you can do it. One is that, so here temp is a column name. Temp by itself is not anything. So if I just write temp here, it would, sorry, if I just write temp here, it says object temp is not found. So there's nothing here as the temp variable. But the way the function is defined is that any column name defined here, any term that's defined here is going to be considered as a column name of this data frame. So if you are to write a subsequent power of this, let's say temp to the power 2, so it's not directly you can write yd dollar temp or something like that. So it's of this form, that temp to the power 2, and you say that make it like an independent variable, consider that independent variable. So you write this I function here. So it becomes yield tilde temp plus the second power of temp from this data frame. So we save it and we write summary. So we see that, okay, we've got some values and we've also got that each of these are significant. All right. So that's this. Another thing you can check here is multiple R square value, right? Or even the adjusted R square value for that matter here. So it's a good enough value. So we'll continue with this. Another way to do the same thing is that, so like it was discussed, if you have to write a lot of power, it becomes tedious. So you can just mention that using the poly function here, you can just write that take this column and make powers up to 2. So the power 1 as well as quadratic. If you run this, you will see that it's giving the same output. And we will use this form to make a cubic equation. We run this and find the summary. And here you can see that when this is done, power 1, 2, 3, they again, so if you can see the dot here, it means that if you take a threshold 0.5, 0.05, then it's not significant. But if you take it as 0.1, then it's significant. So the p-value is somewhere between 0.05 and 0.1, as you can see here. So it is not a very highly significant value, but nevertheless, and especially what you need to see here is that when you take the third power, it's not significant at all. So you can check this with power 4 and 5 and so on, and you would see that these coefficients also do not turn out to be very significant. All right. So therefore, we understand that it's of the form, it's a quadratic equation. So the highest power is going to be 2. Now we want to fit this here, right? So if you remember when we were dealing with logistic regression, the way this was done is that if you can already plot using the summary function itself. The LM function, the output of the LM function can directly be used into abline. But here we no longer are plotting a straight line, it's going to be a curve. So it's basically we have a set of X and Y points that we are plotting. So we want to take points which are quite close to each other. So let's see. So the seek function here, you have to give the starting value, the ending value, and how many points in between, what interval should these points be differing by. So here we can see we can start off with 50, we can end at 100, and we want the points to be quite close to each other. So let's start with 0.1 and we'll see what difference this thing makes. So we have this X vector, the naming doesn't matter. So we have the X vector, and now we want to find the Y vector corresponding to these X based on our model. So which is going to be this M2A model as we just used it. So the way this is going to work is that you have the predict function. The first argument is going to be your model. So based on this model, what you do is you take these values, and I would like to name this value something, right? I don't want them to be just called XY. So the way this works is that, so the second argument, if you see, so temp is equal to XY, it's just assigning XY vector. It's making a new vector called temp, and it's going to be the same as X and Y, XV. And when we say data frame, so what it does is, if I just run this separately here, you would see it's a data frame, right? It's a data frame with a single column, and that column name is temp. So it's just the syntax in which predict takes up values, and we want it to be giving the response of this response of these values based on this model. So we predict. So we have both the values for the x-axis, y-axis. Of course, the number of values should be same. They are paired values. So now we just want to plot this. We want to plot a line based on these values. So it's going to be this line. Now, let's try a couple of things just to make the thing clear. So instead of lines, if I would have just used the plot function itself, right? So let's say I plot this again. So just remember that lines, abline these equations, and also this one, points. I just want to add a few points on this. So these need to have a plot already there behind. They cannot make a new plot, right? They're just plotting points or plotting lines on this. So if I just plot this, so you can see each of this is a circle, right? So it's the same thing. Either of the things can be done, but of course, plotting a line is better. Now, let's try one more thing here. If instead of 0.1, let's say if we would have taken 1, right? Or let's say you would have taken 5. So you see this line is now slightly crooked. You can see it's not a straight line because there were points 50, 55, 60. So it's just joined these points. It's not a very smooth line. So just remember to, if you are to plot this, then plot enough number of points so that it's a curved. It's a smooth curve. All right. So this was the way where we use polynomial regression to find out the best fit model. The next example is where we used the nonlinear least square methods. So let's read the next data set here. Here it is similar. So over the different weeks, the mass of a certain plant, the dry weight probably is measured. So let's again just quickly see what the plot looks like. So it's a typical growth curve, increasing and then saturating. And from growth kinetics, we know that it would be something like an exponential form. So we're going to fit this model to it. And so initially we had discussed that not all functions are there by default in R. As in when you require more and more functions, you need to install a few packages. And every time you want to use them, you would need to call the library. So this command right here can be used to install the package. When you're installing, of course, you need to have internet connection. And then you call the library. You don't need to install packages again and again. If you try to install it again, it will tell you that you already have it installed. So we are not installing it again. So now the function here is NLS capital LM. So there is another function from the same package, which is NLS.lm. They do the same thing, but the syntax is slightly different. So just be careful. So the syntax that we are using here is going to be NLS.lm. It's the same. Yeah, sorry. So it's the same example as was discussed in the lectures. So we have our two columns here, week and mass. So we say that, okay, predict mass, and the equation we want to fit is mass, which is, and it's A times 1 minus exponential minus B times week. And this is the data frame. And here we want to, for both A and B, we want to give a starting value to it, just an arbitrary value, so that it has a certain starting point. So we run this, we save it in EM, and you find the summary. It looks very similar to what we have been seeing until now after the LM function. So it's estimated the values of A and B. It's also done t-test, and we see that both of these are significant. And so we can proceed with this. So we can proceed with this equation. Same, we would like to create some points. So we can see it's going from somewhere from 0 until maybe 16, 17. You can make those changes. And again, points need to be quite close to each other. So we separate them by 0.1. And it's the same syntax again, the predict function. You give the model, here EM. The next argument is the input values, and you make it as a data frame with the name of the column you want here as the x-axis. The type is going to be response. This, and we plot it using the lines function. What happened? Okay. Just a second. Yeah, sorry. So here it's plot those lines, right? You can see it's a good fit. Okay, so I think we're done with the first part, linear regression, right? Any questions from this part? We'll go to the second part, which is clustering and classification. No questions? Okay, good if you're understanding everything. So, all right, so let's go for this. So now you have a lot of data points, whatever experiment it be. And let's say you have two different, so for example, you have done something like a single cell sequencing or flow cytometry, and you actually know the expression of two genes in each of the cells. So each of the dots that you see here is a cell. It's a data point from each of the cells, and it's just plotting. So marker expression, let's say it's in whatever the unit is, let's say it's from 0 to 1 here, and it's also 0 to 1 here. So you have just plotted these. Now, if you see the two images, ignore the colors, ignore the dotted lines, they are the exact same points, right? So now you would like to make some inference about the cells themselves. So for example, there's a tissue section. So we know that, let's say for example, it's the liver. So liver has a lot of cell types. Now you are saying that, okay, if I know the expression of these two genes, gene 1 and gene 2, I can say something about what is the cell type. So you take the liver section, you make a single cell suspension, and you're able to find out the expression of these two markers, and you plot them. So one way could be you just take a look at the points themselves and you say, okay, these 4 points, they're quite close to each other. These 4 are also very close. These 2, these 6 points, these 4 points, and these 7 points. So I am probably think that, okay, so what does this group indicate? It means that, okay, this group has a marker 1 expression somewhere around here. Marker 2 expression is this. So they are quite close to each other. Now the expression is not going to be exact. If it's 0.1 in one cell, it's not going to be 0.1 in another cell of which is the same cell type. This variability always exists. But they look quite similar. They're literally clustering together. They're coming up together in this plot. So I would call them, that is cell type 1. I'm coloring them red. Likewise, these two are same. They look quite close to each other. These two are, and so on. So you make these 6 clusters. So what you've done is, based on distances, literal distances between these points, you have segregated or grouped them into some sets, right? The second way you could do it, you already know that, okay, maybe through some prior experiments, you know that there are certain thresholds. If marker 1 is low expression, versus whether it's high expression, and when it's marker 2 low expression versus high expression, there could be these 4 types of broad categories. So hence you just colored the cells like that. So in that case, you would say, okay, maybe you actually grouped this. So there were these 2 clusters initially, but from this prior knowledge, you know that, okay, when this is the, when it's higher than this threshold and higher than this threshold, they are going to be this particular cell type. So there could be a reason why these 2 cells have been a little distant, but it doesn't make them a new cell type, right? It maybe it's just a dividing cell or something like that. Like same is the case with these 2 clusters. So whether you have prior information about your data or not, you can do unsupervised or supervised learning on them and can group them. They're both ways to group your data points into sets, because this is especially important when you have a large number of data, but you have small groups that they can be classified into or clustered into. Broadly, the concept is same. It's just the inherent algorithm that's different. So here we'll be just discussing more qualitatively about this in the next week. If so, the week 7 lectures are already out, so you would see that we go a little more into detail of each of these things. All right. So we first talk about clustering, which is unsupervised learning. So again, just going conceptually. So one type of clustering could be, so one way in which you can cluster is either you start off by considering all the data points to be independent, all the points are different, there are no groups, and then you make clusters out of it. So you start with as many clusters as your data points, and you keep fusing them and say, okay, these 2 look similar. Okay, that's one cluster. And you make bigger and bigger clusters. The other end of the spectrum could be that you start with all the data points, consider them to all belong to one cluster. And then you say, okay, maybe these 3 behave different, so we can make a smaller cluster out of this, and then these 2 become different, and so on. So that's agglomerative versus divisive clustering. Another way in which this could be done is flat versus hierarchical. So if you remember your heat map from a couple of weeks ago, you remember that there were these dendrograms that you see, which you might have also seen in case of phylogenetic trees, right? So let me just show how that looks, right? So if you this, right? So you have these different points, right? Sorry. So these different points are there. Yeah. So let's say when you clustered these cells, when you've called these two to be same. So let's say you are able to say that, okay, maybe marker 1 expression is a bigger factor of separating cells, and marker 2 is maybe like a maybe it's not as strong a factor. So what you can say is that, okay, low and high expression of M1, they become so something like 1 and 3 and 2 and 4, right? So this separation right here was based on marker 1, and then each of these were based on marker 2, right? So something like this. If you just call them 1, 2, 3, 4, you don't know any relation between them, that okay, 1 and 2 are closer to each other, 1 and 4 are closer. But now when you have this, you can say, okay, 1 and 3 cell types, maybe they're similar, because marker 1 was a stronger, something like that. So that can be flat clustering or hierarchical clustering, right? So this is hierarchical, and if this is not there, then it becomes flat clustering. All right. So when now we want to cluster them, we talked about distances. So distances can be, distance is nothing, but it's measuring the closeness of your data points. And we know that data, so until now, these two figures that we talked about, they were just two-dimensional data. You had marker 1, marker 2, something like that. But of course, you can have n-dimensional data. There could be a lot of markers that are there. There could be maybe the whole gene expression pattern itself. So you can have 20,000 genes that are determining. So we'll also talk about how, so dealing with so much dimensions is also tough. So in subsequent classes, we will talk a little bit about dimensionality reduction. But nevertheless, for the purpose of this course, this class today, so let's say that we have an n-dimensional data. So there are a lot of different distances you can calculate, and why each of them is used varies slightly. So let's just see how this is. So Euclidean distance is the simplest distance, which is the distance between these 2 points. So since you are squaring the difference, so right, so before that, so here x1, x2 until xn, these are the coordinates of the first point. So don't get confused. X and y are not the values, the x and y axis values, right? So you take the first axis, which is 1. So x1 minus y1, square it up. Then you take the second axis, x2 and y2, x3 and y3, square each of these differences, sum them up, and find the root. That becomes the Euclidean distance. So mainly the purpose of squaring was to remove the effect of a negative or a positive sign. This can also be done when you take a mod. So in that case, you just sum of these mod values and you don't need to find the square root or anything. Same is another pattern. If you find any power of it, and again, the modulus is just to ensure that odd powers do not retain the sign. So you find any power of it, and then you add them up, and then you subsequently find that root of it. So this Mahalanobis distance, this is, so if you remember, whenever we talked about like marker 1 and marker 2, so what if marker 1, or that was the gene 1, it actually controlled gene 2 itself? So then it is similar to our problem of multicollinearity. We are assuming these are different things, but they were not really. They were not independent. So in that case, so typically whenever you have these predictors, so in that case, marker 1, marker 2, you would want them to be independent. You are assuming they are independent. But in case they are not, and you still have to consider those, then this S matrix here, which is the covariance matrix, this is going to help negate the effect of this dependence. All right. So this is just, so this is how this distance is calculated. Another way can be that when you have these 2 points, you make the vectors out of it, something like this. And then you actually find out the value, you use the cos alpha value, And using that, you're able to find out the distance. That's the chord distance. Another distance can be calculated as using the correlation between these two vectors. So wherein, so this is typically, it's the Pearson's correlation, and you can find the correlation distance between them. Finally, there's another thing, which is Hamming distance, which is not, as of now, we can't use it for these values because x1, x2, and all of these are going to be just numbers. So this is more appropriate for strings, for characters. So as was the example between, let's say, rat and cat. So the first letter, so you take each of these positions. So the first position, x1 and y1, r and c, they are not equal. So the delta 1 is equal to 0. Then a is same. So delta is, this should be 1. Right? So 0, and then you add 1, and then add 1. So the Hamming distance between rat and cat is 2. All right. So that's the distance matrix, distance measures for clustering. Okay. So this brings us to an end of clustering. Now let's talk about classification. So let's take the example of two cases that were discussed. One is you have cholesterol levels of people from a population, and you would like to use that as a measure of whether the person may have susceptibility to a cardiac disease or not. So here, the presence and absence. So when you talk, so here we first start with a training data set. That means you already know both the things. You know the cholesterol level, and you know whether or not they have a cardiac disease. So presence and absence, this can be like a binary value, 0 and 1. And you can also call it, since it's already scaled between 0 and 1, you can say that, okay, let's call it probability. So there are two classes you can define here. One can be where there is a disease, and the other can be where there's disease. And typically when this like a null hypothesis can be defined, so like a null model, so model 0 is generally that there is no disease. So here in this case, you had just one predictor, the levels of cholesterol, and you had just two models, 0 and 1, right? The null model and the alternate model, so as to say. But you can have, your data can have more predictors, right? We talked about two marker genes. Maybe you can have 5, you can have 10, you can have 20,000 genes. And when you talk about what you want to predict, you can have information about the cell state. So one of the examples is you can have cells which are epithelial, they can be mesenchymal, or they can be somewhere in between, right? So you have 3 classes. So whether you have just one predictor or you have more predictors, whether you have just 2 models or 2 classes or multiple classes, that's possible. You need to classify data. There are just a few different tricks you can use to model this more easily. And normally what it's done is that a logistic regression model, which follows this sort of a sigmoid function, and with this equation right here, it's used to connect your classes to your training data set. And for sanity check, you can, as we'll see in one of the examples, you can test it back on the training data set and check if you have a higher sensitivity and specificity, right? So that means false negatives and false positives should be as low as possible. Okay. And then finally, this can be once the model is set and once you're happy with the model, you can use it on your test data set. So a little bit about logistic regression. So we talked about this equation right here, right? So your input is xi. So when the input is xi, we're calling this like a sigmoid function, denoting it by sigma xi. So this probability is pxi. And this basically means, so we are talking in terms of our alternate model, that the probability of it having that disease, it belonging to your model 1, given that x is xi. That's the probability. And the null model would be the opposite of it. And since these are the only 2 models, the sum is going to be 1. So you can say that if this was pi, this is going to be 1 minus pxi. And if you remember from how we used to denote binomial, so this is like your p to the power of the number of times this is happening, and this is 1 minus b, or q that was denoted there, right? And we know that y in this case can only be 1 or 0. There's just two options. So it's just encompassing both these equations together. And if you rearrange them, so this power that you see here, e to the power minus, within brackets you have a plus bx. So that is nothing but log of pxi upon 1 minus pxi. So this is the probability of the event happening. This is the probability of the event not happening. So these are the odds. You're taking the log. So log odds, it's like a log odds ratio. And another important calculation related information is that specifically for this value to be 0.5, so halfway, then xi is actually going to be minus a by b, these two coefficients. So like we discussed in case of nonlinear regression initially, when you want to fit this kind of a model, you would like to predict the values of a and b. And so once you have the model, so here in this case, when you want to fit the model, there we took example of reducing the sum of the squares of residuals. In this case, we actually want to maximize the likelihood of a model, how probable the model is, right? So in this case, you are actually multiplying all these probabilities for each of your values. So it's multiplication. This is noted by this symbol right here. So if this is maximized, your log L is also going to be maximized. It's just simpler to calculate log L. So this is the mathematical form of it. And so this was the case when you have just one independent predictor, right? X in this case. And if you have multiple of them, it's just the same form, but it's like a plus b1 x1 b2 x2 until bn xn, right? And likewise, the log odds is also just what is there inside this bracket. So this is the case when you have multiple predictors, and when you have multiple classes, multiple values, you can have more models, each of them being a binary form, right? This was already explained in the classes. All right. So before we go on to the practice problems, we have a few more things to discuss in R. Okay. So this was again the same example that was used in the lectures. So we have the training data set here, we're calling it C. So we have information whether the tissue that's there is malignant or not. And we have the radius of the cells and the area of the cells. So let's try plotting each of these one by one. So if we take the area, then you can see that lower area malignancy is mostly 0. And if the area is larger, then the malignancy is mostly 1, which is sort of expected from the biology of the tumor. And likewise, if you take a look at the radius of these cells also, then you can see that, okay, that also follows similar trend. So since we started off the discussion by taking just one predictor, let's start with one predictor, only the area. So instead of the LM function or the NLS LM function, here in this case, we use the GLM function. And the syntax is very similar. So you have the y-axis, tilde the x-axis, the name of the data frame, and this is important. So this ensures that you're doing a logistic regression. And let's save it as L1 and find the summary. And you can see that the two coefficients here. Hello? Any question? So you can see that these are the two coefficients, right? You remember A and B, and this is A, this is B, and both of these are significant. And so here, just remember this AIC value, 300. And so let's just try fitting this model here. So we are fitting the area here. So we just want to make this plot as the one with the area. So here, this one's there. We take a few points. So here it's between 0 and let's say 0.4 or 0.5. You have to make really small distance between them. So I've taken it as 0.01. And now if you remember, so here, when we took the summary, so you see there are these different, you have something about call, something about deviance, coefficients, and so on. So we take specifically the coefficients of from this data, right? So what we do is coef. So if you write just coef L1, coef L1, you would see it has two things. So this, if you take a look at the structure of this, it's like a named list. So the first element is this minus 3.57 and its name is intercept. The second element is 34 and the name is area. So it's just, this is how you call a named list, the elements of a named list. So we know that, okay, A is going to be our intercept, B is going to be the coefficient for the area, area values, and we have XV, A, B, and we can plot the, we can calculate the corresponding values because we know the equation. And yeah, so we can just make the lines. So you can see this is how it's plotting. If in case I would have taken, let's say 0.1, so you see it was a crooked line, right? Because it took value at 0, it took this, 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 and this. So it's not fitting. So you have to, when you want to plot it, you need to have enough lines, enough points for the line to be a smooth curve. And now normally the threshold is set as 0.5. So when would this value, this probability value be 0.5? We already know that's going to be minus A by B. So we just make a vertical line at this threshold using the avline function. And this, so we can say if the cholesterol is greater than, let's say this was, so you can see what the value of thresh is, it's 0.1028. So if the area is greater than this, then you can say that there's a higher chance that the tumor is malignant. But if the area is less, you can say that it's probably not malignant. And now we would actually like to find something that is known as these sensitivity and specificity. So what we do is that based on this model, because we just said that greater than 0.5, less than 0.5, and so on, let's predict. So what we'll do is, so what this predict function is doing, it's taking our model, right? We call it as L1, and it's taking our data frame, this thing, and it's saying, okay, calculate. So if you take what P1 looks like, it is these values, the probability values. And our model is that if it's greater than this threshold, greater than 0.5, the probability, then you call it as malignant, that means 1. So you're basically converting probabilities from a continuous set to a binary set, right? So P1 initially was these values, and now you can say that P1 is 0 and 1. These numbers that you see here, they are just indices. Again, these are named lists, but you don't need to worry about that. So a confusion matrix is a 2x2 contingency table, wherein if you see, so actually you had 0 and 1 and you predicted 0 and 1. So these, can somebody tell me, so you have 4 options: true positive, true negative, false positive, false negative. Can you tell me which of these 4 are what? What is 274 here? So in reality, it said it's 0, so it's not malignant. 274 is true positives, right? What is 135? So let's say this is also in a way it's also like a true positive, right? Because it correctly predicted this. So we can call 274 as true negatives because 0 actually meant non-malignant, so a negative test. So That is why we can call 0 as negatives from the actual case, and 1 means positive. So 274 can be 2 negatives, 135 can be 2 positives. What does 41 here mean? So these 41, in reality, they were positive, but they were predicted to be negative. So they were negatives, right? You predicted them to be negative, but actually they were false. They were not negatives in reality, right? So 41 becomes our false negatives, and 20, they were predicted to be true, but they were actually not, right? So they were false positives, right? So these 4 things, these would come really handy whenever you're dealing with this kind of data. And we want to find the specificity. So specificity is this divided by the whole thing, right? So specificity is, I think, the true negatives, right? And this is, so true negatives by all the negatives. Yeah, true negatives by the background, true negatives and false negatives that were there. And this is going to be specificity, and this is going to be sensitivity. So you can see these are good enough, 93% and close to 77%. But we know that we missed the predictor here. We would also like to check if both area and the radius can together make a better model. So here we just used area. You can also try doing this with radius. You would get similar metrics, but we'll see that when we take both of these. So again, the format is same, GLM, the y-axis, tilde, each of these from this data frame. And we want to make a logistic regression model. We find the summary. You have now one more coefficient here. Each of these are significant. And this AIC value, the lesser the better. It's like an error term. So we know that AIC, using the AIC metric, this is a better model. And we would also like to see using the sensitivity and specificity values here, doing the same thing. So we can see that specificity has increased from 93 to 94, and the sensitivity has actually increased from 77 to close to 87. Now we would like to see, so we used some data points, right? So if you remember, this has 470 observations. And these were actually the values that we know. Now let's say we have made a model and we would like to give it to the doctors, and they have these tissue samples. They can calculate the area, average area and average radius of cells in that area. And they have these values. So if we send it to them, now it's going to be a different data. These were 470 patient data. Now more people come to the hospital and they get checked. So we want to check if this is actually going to work. Currently we made a model and we tested on the same set of data. Now, does it also fare well on a different data? It's a random different set. So we check this. Now, here you see it's looking the same, right? Because this was taken from the same same initial data set. But typically, this information from the test data set is missing, right? It is a test data set. You're actually using your model in real life settings. So you would not have this information. But for the purpose of showing it here, we have this information with us, and we would like to check if our model, which we made from the training data, works well on the test data. So we've read this. We already have the model with us, right? The L2 model. We are not making a model again for this data, but we want to predict the effect of this from the test data. So it's going to take the area and the RAD variables from this new data set, and it's going to find P3. Again, we are making P3 binary. It's going to be malignant or non-malignant based on whether it's greater than 0.5 or not. And we make this confusion matrix, and you see this. So test data had 99 observations. So out of 99 of them, 89 of them it's able to predict correctly, right? So true positives and true negatives are very high. Nevertheless, we calculate the specificity and sensitivity, and we see that these fare pretty well. So you trained on a different data, you are testing it. And this is just for our check. It's just for reference that whether here we have actually did this model correctly predict. Okay, so this brings us to an end of both the sections of this week's classes. Now we have a few practice questions, but before that, do you have any questions? Anything that you would like me to explain again? Typically, null hypothesis is a negative statement, mostly, but it's always good to define it. Right? Like in this case, when we were talking about true positives and true negatives. So it is based on the situation. Whenever you're doing a test, presence of a disease is considered as a positive outcome, and the absence of a disease is a negative outcome. But you always should define, whenever you're defining a model, it's always good to mention it so that there is no confusion. Otherwise, like in this case, 0, 0 and 1, 1, they are both, like they are correct, right? Trues. So anything can be considered. Any other questions? Yeah, all right. Okay. So, yeah, all right. So this question, if you have a paper and pen with you, please calculate. I'll give you a minute or two for this, and then I'll show the calculation on screen. So the equation is, if you can recall, it's similar to one that we discussed a few minutes back. So the equation is V is equal to nu upon 1 plus u. So u is our predictor, V is the dependent variable of the outcome. We want to perform linear regression, and to perform it, we would like to linearize this equation of the form y is equal to ax plus b. And as you can understand, this is going to be y. So you would like to know about a and b, and additionally, please also tell me what is x here. So if you please calculate. In the meantime, I'll also start solving this. Right, so here we are just going to inverse this. So it's going to be 1 by v is equal to 1 plus u by mu. So you can take this 1 upon mu plus u upon mu. This gets cancelled. So you have 1 by m, 1 by u plus 1 by m. This is 1 by, so it resembles this form. So here this becomes y, and of course u is the initial independent variable. So 1 by u becomes x here. So you can see what are a and b. So which option is correct? Option A, right? All clear, right? I'll move on to the next question. So you are performing a polynomial regression for a data set, and you have these two models, just like the one that we discussed in R. So it can be either quadratic or it can be cubic. And you would like to perform ANOVA to test which of the models is correct. What is going to be the null hypothesis? So is P3 0? Are P2 and P3 equal? Is P2 0, or are both P2 and P3 0? Why do you say option D? Could you elaborate on why you think option D is correct? So if you remember, when ANOVA is done on successive powers of successive degree of our equations, we want to check if this model fares better than this model. So that means, what is the difference in these two models? It's about P3. So we only want to check if P3 is 0 or not. Right? Because if P2 also becomes 0, then this equation is also incorrect to begin with. Then we only should have used a linear model, right? So you just want to compare two models wherein you want to see if the two models are different and what makes them non-different, this thing. So therefore your null model is null hypothesis that the two models are the same, which means P3 is 0. All right. Okay. Which of the following statements is incorrect? So when you classify data, it requires labeled training data. When you cluster, that is an example of unsupervised learning. When you classify data, that's an example of unsupervised learning. And there could be something known as semi-supervised learning, which also requires a set of labeled data. So which of these is incorrect? So remember, clustering, grouping, classification, you have metadata. So which equation, which statement is incorrect? See, so when you classify data, so classification is a form of supervised learning actually, because you have metadata, right? So yes, so option C is incorrect here. Good. Okay, now we have three predictors, P, Q, and R, and we want to fit a logistic function for sigmoid function for logistic regression. So if you remember, which of them closely resembles the sigmoid function? So A, B, C, and D. Which of these? B. That's right. Okay, so this is the form. Very good. Okay. All right. So now we want to classify cells as differentiated or undifferentiated. And there are two genes, NANOG and OCT4. We want to use these two expressions to classify them as these two states, and we will use logistic regression for the classification. What is the kind of data you need to begin with? So the gene expression data from two separate types of cells, one which has only differentiated cells and the other only undifferentiated cells, or you would need data from only differentiated cells and not undifferentiated ones. You would need it from a mixed population, which has both types of cells, and you would need expression from a cell type which is neither differentiated nor undifferentiated. C. So could you elaborate your answer? Why do you think C is correct? So the important part is you want to train. And what you finally want to do is classify. So if you remember the case of cholesterol levels and cardiac disease, you had values. So in that case, there was just one predictor, cholesterol level, but you knew which patient has a disease and does not. So these two information were available. If you have gene expression from a mixed population, which has both, then you don't know. To begin to actually assign them as differentiated or undifferentiated, you would need another model, right? So the thing is, you need both. You need differentiated also, and you need information from undifferentiated cells also, but you need separate information, right? So in that case, A is the correct answer. You have a cell population which is only differentiated. You find out the expression of NANOG and OCT4, and you understand, okay, when, let's say the expression is 0.5 and above for one, and maybe 0.7 and above for the other, then I call it undifferentiated. And when these expressions values are lower, then maybe I know that they are differentiated. So something like this. Let's say this was NANOG, and this one here was OCT4. So you understand that, okay, you have two kinds of data. So when you plot, when you had undifferentiated cells, you saw, okay, typically both the values are higher. And when you had data from differentiated cells, so this is differentiated and this is undifferentiated. So you know that, okay, normally these expressions are lower and this is higher. Now when you want to classify cells, when you have a mixed expression level, and then you are able to, let's say, you have these different points, then you know, okay, maybe these ones are differentiated, maybe these ones are undifferentiated, something like that. Okay, so to begin with, you need to have an expression from two different values, right? So remember the case of patients. You knew that there were malignant people who had malignancy in the tumors and those without malignant tumor, right? In case of cells, they need to be calculated separately because single cell information can be retained when you do it separately. Okay, and this is the final question for today, I guess. So you want to calculate the chord distance between these two. So let's just go back and check. So this is the chord distance, right? Root of 2 multiplied by 1 minus cos alpha, where cos alpha is the dot product divided by the norm of these two, right? So chord distance is 2 times 1 minus cos alpha, where cos alpha is x vector, y vector, and the norm of these two. So can somebody calculate the dot product? So I hope you remember how the dot product is calculated. So what's the value of the dot product to start with? 2 multiplied by 0 is 0. 0 multiplied by 2 is 0. This numerator becomes 0. Therefore, cos alpha is also equal to 0. So plug in this value here. So you write 1 minus 0. Find the root. So it becomes root of 2. Now it says that you have to write your answer until the third decimal. Now, there's one important thing. So if you have taken a look at today's announcement about the exam, so they've mentioned that an on-screen calculator will be available to you. So let's just try to find root 2, because just to be sure, we'll write 2, we'll use this, we have this value, we want to find it to the third decimal place, so it becomes 1.414. All right. Okay. Yeah, so there was question 7. This was one of the questions that was asked in the last lecture, at the end of the last lecture. So here they wanted to find the correlation distance, that is D-core, between gene 1 and gene 3, right? So just for the purpose of showing it here, so if you remember, yeah, so correlation distance is 1 minus core upon like the half of it, and this is Pearson correlation, right? So I have it here. So these values, just reading in these values again, gene 1 and gene 3, you see there are 5 values each. So can you quickly tell me what function do I use to find the Pearson's correlation? It's the core function, right? So core, you write the first value, you write the second value, and just to be sure, you write Pearson, and let's save it as well. We read it, we get this value. So the distance is 1 minus val, and we take the half of it. So it's going to be 0.94. All right. Right. So just to describe it here, right, so we can calculate Pearson's correlation, and then use 1 minus core of gene 1 and gene 3 and divided by, right? All right, that brings us to an end of this week's live session. The session was recorded. I'll upload it to YouTube. The script and the PPT that we've used today will be uploaded on Google Drive. The deadline is day after tomorrow. Day after tomorrow is also holy, so please don't keep it until the last day, right? Please, if the questions are clear, if the concepts are clear, please go back and do it by tomorrow. And right, so we'll meet for the next live session on next Monday, same time, 6 o'clock. Yeah, let me know if there is anything else you'd like me to discuss. I'll stop sharing my screen now, right? Yeah. Any questions, anybody? If there are no questions, then we are done with today's session. Thank you. Thank you for attending. All right. Bye-bye. I'll end the session. Thank you so much. Bye.